Okay, this is the first time I've tried this kind of recording thing. So I'm going to try and do a walkthrough of the code for the Raspberry Pi guitar amplifier. And first, a quick run through for to show what it is I've got here. I've got a Raspberry Pi back here, and it's wired in all kinds of crazy, which we'll get to in maybe a different video because I don't want to try to mess up the cameras I've managed to pull together. Connected into this old Vox cabinet that I originally might have destroyed. This was the original, there's a bodge wire that someone, I'm not admitting anything, might have attempted to do something with, and it failed miserably, so I went the route of rebuilding the amplifier with a Raspberry Pi. And I'm having trouble with the volume level, so we'll do the best we can here. But to give a sense of what it sounds like, this is the guitar. And I'm trying to make a better audio signal by putting a microphone directly up against the speaker grill here. So it's got a delay effect. It's got a what's the delay? Turn that off. We've got a reverb. Very shimmery reverb. It's my favorite effect. We've got some distortion. And we've got a wah effect, auto wah. Let me try and turn that up. And we've got your tone controls and a wet dry setting and a overall master volume and some LEDs that light up. And some LEDs that light up here. That's sort of attempt to show the volume. So that's how it works. Let's go to what the code looks like that runs this. So it's running over here in a window. This is a SSH terminal into my Raspberry Pi, which is sitting over there. This is running on my Mac, which is over here in front of me, which you can't see, but over there. A separate monitor, I've got the Raspberry Pi, and I've got a TMUX session, and TMUX is a terminal multiplexer because to make the Raspberry Pi be able to do the guitar effects, I took out almost everything else. There's no GUI, there's no wireless, there's no Bluetooth. All those services have been stopped to give it enough oomph to be able to do the audio processing. And even so, there's probably some additional audio distortion happening because I'm running SSH against it, which is minimal, but taking a little bit of the resources. So we can look at the program. Micro is the editor that I use as a terminal editor. You could use Nano, you could use VI, you could use Emacs. I'm using Micro. Micro is a simplistic one. It has a nice highlighter for Python, so I can at least look at it. I did most of the development on VS Code on my main computer and then pushed it over to the Pi. That adds also all kinds of audio latency, so I'm showing it just running on the Pi here. So here's the program. The first line is a shell script bang to say this is a Python file, run it with Python 3. The next line is a comment. So here's the parts where we get into it. So GPIO 0 is a library for handling the controls that are coming in and the LEDs that are lighting up. So the MCP 3008 is a chip that takes inputs from things like potentiometers and turns them into digital signals. The Raspberry Pi by itself doesn't have a analog to digital converter like a like an Arduino does. So that chip is wired in here. I have all the details on a Google slide document, which I'll link to also, and I'll run through that separately, probably in another video. Um, and then we've got the LED board, which is used to do the volume LEDs over here. Those ones I glued into the front. And I'm sorry, that's wrong. LED board is for me to do the LEDs on top. An LED bar graph is the ones in the front. So LED board is the one that lets me light up the individual LEDs in response to how much I've turned each potentiometer. Signal, time, and argparse. So argparse, working backwards, argparse allows me to put parameters into the application for debugging because there was a lot of debugging and a lot of stuff that went wrong. Time is so we can have a sense for how long the thing has been running. I'll show you that in a second. And then signal is used to handle any keystrokes that come in so we can stop it. That's sort of the main thing. My dog just walked through and moved some stuff around. See if she decides to come back on camera. And then PIO is the main library. PIO is the audio processing library by, I'm going to hope I say his name right. Oh, there's my dog barking at squirrels. Olivier Belengo. I probably said that wrong, but it's absolutely amazing. It's basically a library into a bunch of C functions for doing audio processing at high speed, and it's a Python wrapper. It's absolutely amazing. It does a bazillion things. I've used a tiny fraction of them. So the first part up here is the argparse, where we're taking in arguments to say, are we running this in debug? Are we running it in, are we running it where we want the LEDs off because I wasn't sure if the LEDs were causing other delays or problems, so we could turn those off. And then we can have a VU meter. So I'll show you what that looks like by going over here. And I can remember my commands, Control B, like, no, Control B. Make sure I'm in the right, there I am, okay. I'm in the right window, I'm in the other side of the terminal. So that's where I'm using, you can see where the time is being used. We had fun for 1,387 seconds, 0.21. And I can say, I can run the command pedal master. Well, I'll run it directly from Python 3. I remember if I did this right. Pedal master .py, and I'm going to say with the VU meter. Yeah, so proof I'm doing this live. So now it's running with the VU meter. Let me try and change the, yeah, that's gonna mess up. So I'm gonna try and change the width here. So I'll restart that. That didn't work out so well because I changed the width of the terminal there. There we go. Okay, so there's the VU meter. And I did that so that one I could see if it was working and figure out how to get the VUs and then connect it into the LEDs later. So again, a lot of the coding here was to get the thing to work. And if I go into debug mode, it's telling me the value of each potentiometer so I can see what the hell's going on. So as I turn a potentiometer up or down, I can see the value. Now, in my first video, someone noticed I had all the potentiometers going backwards because I apparently, as a genius, had wired them all in reverse, at least consistently, and then had to change the code, which we'll get to in a second. So turn that back off again, come back to the code, and we can see, let's see here, clear this other side so it's not making a huge mess over here. Okay, so back over here, we've got these debug LED and meter lines are simply reading the parameters that came in from argparse. So if you don't need any of that argument stuff in the command line to try to debug or do anything else, you can leave all this out. I think that's an extraneous line I don't use anymore. I had tried several different ways of polling the potentiometers to get their values, including doing it at a set interval, like every half second. So that's a remnant from the past that I gave up on that approach and simply pull it now continuously as fast as the Pi can. I thought maybe it would reduce audio latency to check it every half second, but it just was distracting that you turn the knob and then have to wait for something to happen. It was noticeable. Number of lines, 8. That number of lines is the number of potentiometers I have. The pot LEDs is the LED board 427. So each of these numbers is a Raspberry Pi GPIO pin number. So I'm saying that for Raspberry Pi line 4, GPIO line 4, that's going to connect to the first LED. And then I could sync up that the first LED is going to be the one that's associated with, I think, the dry wet mix. And then this pulse PWM means pulse width modulation. That's true. PWM equals true allows me to change the brightness dynamically and not just on or off. The VU LEDs are the ones in the front for volume, and that's an LED bar graph. And again, these are GPIO pin numbers 4, 16, 25, 6, 5, and 17. And again, I'll link to the Google document that lays out exactly where each of those GPIO pins is used. I think I used all but one of them. So that's what that is. And then potentiometers, I'm saying that we're going to have a Python list that calls the MCP 3008, and for each channel in the range of number lines. So we're going to get 8 values from each potentiometer, and that's setting up the potentiometer list or array at the beginning. And then the values of them is going to be 0 times num lines. I'm realizing that's probably not the best Python practice here, because what I'm doing is I'm making a list of 8 zeros that I can then adjust, the ultimate values of what I want to process. But in Python, that makes one object. Each of the copies of the 0 is one object as opposed to being multiple objects. I probably should have done that with a list comprehension, but it doesn't seem to cause a problem. Well, there's something to check on later. So now we've got some functions. We've got a control C handler and an RMS meter callback. I'm going to skip ahead and come back to those because they get called on later, and then I can explain why they're up here. So maximum RMS. RMS is a measure of volume. It stands for, I believe, root mean squared, maybe. But it's a measure of the amplitude of the sine wave, and it is a function available in PIO to get what the current volume is of the signal. And I'm setting it at 0 because what was hard to do was to get the VU meter lights to go. If I played loud, I wanted it to go up. If I played quietly, I still wanted it to register. So I've only got 5. So keeping some sort of reasonable range, I keep that max RMS moving up and down over time so that if you start to play quietly, the meter sort of resets itself to the quiet level. The VU factor is 1. We'll see what that is in a second. So now we got the stuff for setting up PIO, and this is the heart of it. This is really all the audio effects. And it's, again, amazing what this PIO module does. So first, I'm calling the PIO object server and boot. So server creates an audio streamer, and boot tells it to start. And then I start it. Well, boot initializes it and then starts it, and you can also stop it. So you can put the start right on the same line. I went back and forth in all the documentation on the PIO website. He's got start as a separate line. I don't know why, but I put it as a separate line because I didn't want to break anything. Some of that programmer, I don't know what it does exactly, why it does it that way, so I'll just copy the code and do it how it looked before. Audio is going to be the PIO input, and dry is going to be the PIO input. So I'm going to need both for the wah effect. So I've got the audio coming in from the guitar, and it's coming in, and it's going in through a sound card, the audio injector, again, in the Google document. That's where the sound injector information is. And which excellent card also. Excellent support on the website. And then the dry is just another input coming from the same place, and they're both PIO objects. So the wah effect, which is listed here first, is the most complicated. Again, cut and paste from some other code with some modifications that Olivier had already provided. So follow is going to follow the audio signal with a it's just following along, and then with a slight delay, and then the wah frequency. I'm saying I'm going to take that follower between 300 and 20,000 hertz, and then to create the actual wah effect, I'm going to take the frequency from the follower, which is the wah frequency in that range, and I'm going to run it through a Butterfield bandpass filter, which is this interestingly named but BP. I didn't name it. And that takes the frequency it's going to use is that varying frequency that has been scaled between 0 and 1. A scale is going to move it between 0 and 1 of that follower for that range of frequencies, and do it with a Q of 30. And Q is a quality adjustment for a bandpass filter. And so it makes this little distorted sound. My dog would like to come back in. So it makes this kind of distorted sound. Paulo, do you want to say hello to the people? All right. Is that your hello? Do you expect a snack? I don't have any snacks here. Sorry. Anyway, back to the bandpass filter. So that is how the wah effect gets created. I take out a particular frequency, it's delayed a little bit, and it feeds back in on itself. And that creates the wah 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 as it fades along. Again, I wouldn't have come up with that on my own. Found it on the PIO website as an example. Much easier to understand is going to be the delay, because it's using the smooth delay. The smooth delay doesn't cause any distortion or audio clicking when you change the value. And because we can change the value with the potentiometer, we want to adjust it on the fly. Smooth delay versus the other delay, which is just called delay in the PIO library. Smooth delay takes the audio, provides a feedback preset of 0.15. I found that worked for me. And that's it. Reverb is even simpler. We're taking the freeverb built-in audio effect, running the delay signal through it. So now we're building a chain. So delay feeds into freeverb. Freeverb feeds into distortion. So if we think of like guitar pedals, this would be chaining them together. At first I had all the signals, all the processing happening independently on the input, which also works, but it doesn't sound, you can sort of hear the dry signal coming through, and then there's a delayed version and a distorted version. So this allows the distort to happen on the delay and on the reverb, and the reverb to happen on the delay. And then the final one is the EQ, and the EQ takes the distortion in, and this says I'm going to take 3 values to split up the frequency spectrum into 3 blocks, and I'm going to multiply each of the parts one by one. So these are initial values. I'll come into how we change them all in a second. And then we've got a wet signal, which is where we mix together all the stuff that has got into that EQ so far. So the EQ is basically the one input to the wet signal, and then the wah has to be done separately. And then I've got the mix where I mix together the dry, the wet, and the wah, and that goes out. So whatever you want to actually play from PIO, that's where you put the dot out method, and that's going to push it to the output. This amplitude equals PIO RMS, mix function equals RMS meter callback. So this is where I'm measuring the amplitude of the signal, so I can use the VU LEDs, or I can produce the output we saw from the meter argument on the program. And here it says function equals RMS meter callback. So this is where that previous function comes in. It's going to call on on its own internal cycle. It's going to do a callback to that RMS callback function. It's basically going to do it as fast as the Pi will allow. And every time it calls it on every loop, and this would be more like JavaScript running a continuous loop, an execution loop, or a game program where you've got a main loop that you're operating. So the PIO server main loop is now calling on a regular basis this RMS meter callback function, and it's providing it the RMS information as a string of arguments. That's why we've got this asterisk args. The asterisk is going to break up that list of arguments into each one at a time being fed into this function. It's going to take the list and break it into its pieces. So I'm not proud of this, but it seemed the most effective way to work. I've got these globals. So I've got the max RMS, the VU factor, and the meter itself. So I'm setting the VU max to the highest value, and then I'll back off. So arg0 is going to be the value at the current moment. And if it's greater than the maximum RMS, which remember we set initially to 0 as a floor, I'm going to set the maximum RMS to that new value. So as the volume came in, that's now the maximum volume. And the VU factor is going to be 20 divided by the maximum RMS. That's because on the screen output, I had 20 bars. So it's not the LEDs, this is just the screen one we were doing before with the meter. And if the maximum RMS is greater than 0.05, then I'm going to slowly back it off. And that was so that as I'm playing it, if I play something loud and it goes all the way, maxes it out at some large value, and I then stay quiet for a little bit, it will slowly work its way back down. You could call it a glitch. I wouldn't argue with you. So if LEDs on, remember, is a argument I can pass. I can turn the LEDs on or off, and by default, they're on. Then I'm saying the VU LEDs value equals a minimum between 1 and the arg0, which is that current volume, and the times the VU factor divided by 20. So that VU factor divided by 20 is going to give me my range for the 5 LEDs I've got. So it's going to give me a number between 1 and something, and then the LED graph function in GPIO 0 takes that number between 0 and 1 and then lights up as many of those LEDs as is represented by a number between 0 and 1. As you can imagine, there was lots of room for mistakes, and many were made. So then if the meter is on, then I want to print this. And then all this jibberty-gook here is printing colored vertical bars. So these /033 bracket 5G03, those are terminal ANSI control characters for changing the color and positioning the cursor. So I'm positioning the cursor over to the left. I think it's 5 spaces in. I think that's what the 5G means. And then changing the color and then printing out a portion of the amp bar between, so remember I got 20 of them. So the first 10 are going to be in green. The next 10 are going to be in, so if I have less than, if I only have green ones, I do the green printing. If I have green and yellow, I'm going to do green, which is 32, and yellow, which is 33. And then if I'm going to have more, I'm going to do green, yellow, and red. Could this have been done more clearly somehow? Probably. But I got it to work, and it's not a major portion of the program. And then this print 1F just puts me back up a line, so that every time I print, I'm overwriting that line of VU bars so that it's not just scrolling forever, like it did when I had the screen too narrow. Again, if you don't care about any of that stuff, you don't need any of it. You can focus on just the guitar effects portion. So I'm going to skip the signal and come back to that, I think. Well, let's start here. Okay. So signal.signal. So I'm using the signal function from the signal library, and I'm saying on receiving any kind of the interrupt signal, which is Control C, call my Control C handler. And my Control C, again, this is a callback function. Signal is also setting up a continuously running loop, so it's another one, waiting for a keyboard interrupt. And Signal can process lots of different kinds of things coming in. I wanted to use the keyboard Python library, but you can't in Linux unless you're running as sudo. But if you're running as sudo, it's hard to set up the Python libraries and bleh. So Signal it is, and Signal allows me to catch the Control C, and then if that happens, I go to the Control C handler up here. It gets the signal number, it gets the stack frame, neither of which is important to me. I don't use either one. I probably could just put underscores there. I've got these globals again. I use globals. Life goes on. I've got samples, start time, and debug, and then end time. Start time was initiated when we started the program. It's a little bit lower. I've got the end time, and I can print out a bunch of blank lines. So long and thanks for all the fish. Print, we had fun for however many seconds. This is an F string in Python, which allows me to put the variable inside a string and format it. And again, I've got the control codes to put it in a different color because I figured out what the control codes are, so I'm not going to not use them everywhere I can. And then if I'm running debug, I can say how many samples per second I was getting. And then I can exit. And I also remember to turn the cursor back on because I turned the cursor off. We'll get down to that part just to keep the screen from flickering. And it also, the less output you're doing, the faster the processing works. Even just printing those potentiometer values, the reason I have that as a separate debug, just printing them out can cause audio artifacts. All right, now I actually do some real code that does something. So all that ceremony to get things running. So I clear the screen and I hide the cursor and I move it to column 5 in case you were going to run the VU meter. I print that we're running the pedal effects thing because when I would log in, because it auto starts, it's in my, essentially my bash start. I use a different shell called fish and it's in my config file and I'll show that in a second. That causes the program to start every time I turn the Pi on. The problem with that is if you SSH in, it starts the audio amplifier, and then if I close it, it just sort of exited the whole thing, and then I couldn't get back into SSH, or I didn't even realize what was happening. I'm looking at the screen going, why is it doing nothing? So it tells me it's running, and I can press Control C to stop. I set my start time to the time. That's all I'm using the time module for is a start and end. Again, if you don't want it, don't use it. Samples are 0, again, just for debug purposes, because I was trying to see how rapidly it was doing that call. I say if you've got the meter, we're going to print the meter stuff out. I'm going to print out actually that I've got that VU and then a line. And then the other call to meter will happen later. And then here's the core loop, while true. This is the heart of it. I'm incrementing the samples. If debug is true, it's a 1 in Python because true equals 1. Of course it does. And therefore, I'm just incrementing the samples every time it runs through this loop. I thought that was nifty. I could have just plus equals 1, and I don't need to use the number. But I figured I don't want samples becoming some gigantic number if you're running it for 6, I don't know how many days you have to run it for it to overflow. I don't know. I was being too careful. So I wired all the pots backward, so that's where the 1 minus 0 comes in to compensate for it. So if you wired them correctly, then you don't have to do that. In this line, this is where we read all the values of the potentiometers. I'm saying the new values equals 1 minus the potentiometer n. Again, that's that potentiometer thing I set up with the MCP 3008 component of GPIO 0 reading those continuously. Again, that's running again in the background, continuously running. Pots n dot value is giving me the value of each potentiometer. I'm multiplying it by 100 and then dividing it by 100 because I didn't need the enormous granularity of the potentiometer. I only needed essentially 2 digits of accuracy was enough, because also as the number sort of went up and down in a slight fluctuation, it would cause audio artifacts. So this is to sort of debounce the signal. It is debouncing the signal. So I multiply by 100, I divide it by 100, and I take the integer values. That gives me a two-digit value. And again, for n in the range of num lines means I'm just going to do this for every one of the 8 potentiometers. Then for I, NV in enumerate new vals. Enumerate takes a list and it splits it into, I've got an index. So if I've got 8 items, I've got item I is going to be 1, 2, 3, 4, up to 8, actually 0, starting at 0, it's Python. And then NV is going to be the value of the item in the values. So this allows me to say, if it's changed by more than 0.05, then increment it. So this is another debounce. So first I reduce the significant digits, and then I say, if it hasn't changed by 0.05, don't change it. And so I've got a new value, and the only thing I'm going to actually use is the value. So nvals, new vals, is the new values. Vals was the existing ones. And I leave vals alone if the new value isn't 0.05 larger. So if you add the absolute value, means you've gone up or down by 0.05. So I think I explained that terribly. You might have completely gotten it and go, well, it's obvious. But the idea is, if I haven't made a change to a potentiometer larger than 0.05, don't record it back into the values. And you might have drift just sitting there. And again, it introduces audio artifacts that change the stuff very frequently. Then I've got my, if I'm running debug, then I can print nothing. And I then print for the range. This is to make it work with the VU meter. If the VU meter is working, I got to put a blank line in. And then I print where the potentiometers, because you can have both the debug on and the VU meters. So a lot of this code is not about the audio, just looking pretty. So if LED's on, then I go for each of the values of the potentiometers, which remember is the vals n. That's the primary list. For each one in the range of the length of the pot LEDs, because as I was debugging it, I would have different ones, and I would try 3 of them. I was just trying to get it to work, so it wasn't always going to go to 8. So it wasn't always going to be in num lines. This was a debug hack that if I only had 2 of them wired up, I could test it. And I'm saying pot LEDs.value, this is turning them on, because this is what's referencing back to that LED board, sorry, the LED bar graph, which is going to cause, LED board, these are the pot LEDs, LED board. Just by changing this number, that LED board function, again, running in the background, will change the lights. And now we do the audio processing. If you've changed any one of these values, dry is going to be potentiometer 0. So it's wet. And the range is going to be 1 minus val 0 is going to be how much dry I've got, and val 0 itself is going to be how much wet. So that I'm, if I've got, and the potentiometers go between 0 and 1. So if I've got fully over to wet, then I get no dry, and vice versa. Delay, I'm setting the delay parameter of the delay effect. So this is a method inside of the delay object, and it's got a value, and I can just assign it to something. And Pio picks it up, because Pio's running that server, again, running all the way in the background, constantly just changing this value to whatever I've set the potentiometer to, changes it. I don't know how far we are into this thing when I finally got to the part that works. 34 minutes. Holy cow. Anyway, that's where it is. Did I bury the lead? It's open source, man. That's what it is. So reverb, again, strictly set off of the size of the reverb is set off of the potentiometers. The distortion drive, I'm using a power function. I'm exponentiating times 0.05. I am a former math major, but I'm embarrassed about how long it took me to figure this one out. I wanted the distortion to ramp up quickly as opposed to linearly, because when it ramped up linearly, you didn't get any distortion until you cranked it almost all the way, and then all the distortion happened at the end. because what distortion is doing is it's overdriving the signal and clipping it at the edges. So as this is your max input and output, and then it's amplifying the sine wave, basically the audio wave, so that it flattens out, which is equivalent of the speaker cone smacking against either end, either being pushed completely out or stuck back against the magnet. And for anyone who actually knows how audio works, I apologize for that description. So the exponential function causes it to follow a curve like to follow a curve instead of being a linear curve like delay and a linear curve. That is not even visible in the slightest. I need a thicker pen. Oh, there's a Sharpie. That should be quite loud. There. That's linear. And the exponential function is causing it to ramp up like that, actually. And we screwed around with the numbers till we came up with 0.05. We being my guitar instructor, Ben, who I built this project with. He provided all of the audio know-how as to what things sound good, because as an expert guitar player, and I worked on the Python and the electronics to realize the vision. For the wah, there's a multiplier effect. I ended up at 30. I tried a bunch of different numbers. This is one you could tune to however you like it. And then the EQ, I multiply each one of them times 2. It seemed to give a better range of turning the each of the frequency ranges up or down to get some noticeable effect. It maybe should be larger. Somebody with better audio knowledge. And then I have in comments all the different functions because we tried a whole bunch of different ones. And so I just kept in the code, here's all of the primary functions built into Pio that we could use. There was a frequency shifter, a harmonizer, and the chorus. We went back and forth with the harmonizer and chorus. I didn't love how they sounded, so I left them out. There's compressing, there's expanding, there's a wave guide, all kinds of stuff. So if you really know what you're doing with audio, you can build a really fancy one. You can wire up anything you want. This is what I built. So let me get out of that and then show you what the config file is. So the primary shell for Linux on a Raspberry Pi is typically Bash, or most people use Bash in Linux. I use Fish. I like Fish. It's got a nice history function. And I just changed my configuration file to add one line. So it's got this thing in the beginning, which is a configuration in case I'm running iTerm, which is what I run on my Mac, because I have to be different about everything. And then Python 3, it just runs it. That's just the first thing it runs. I tried different things. I tried using a service. That didn't seem to work well. I tried doing a cron job thing. That was totally a waste of time. This seemed the easiest way to cause it to start when I'd power on the machine. Trying to think if there's any other piece of information to convey. Again, I turned off a lot of services. So these are the services. Oh, that's not it. Trying to see which ones I've got running. So you can see here sort of my history of turning off various background services to give enough processing power. It was not an exact science. I just kept turning things off. I turned off the DHCP server, which is unnecessary because this thing is just receiving DHCP. It's not serving any. I turned off dbus. I don't know exactly how it would be useful for this application or if it was serving anything important, but it didn't matter because it seemed like the system turned dbus back on anyway. That was probably the one I was most nervous about. I turned off NMDB and SMDB, that was Samba file serving. The only way in and out of this is SSH. So if I want to move the primary program off or on the platform, I use secure copy through SSH, SCP. And I turned off Pipewire because of the version of Raspbian I was running. It came with Pipewire, which really conflicted with the audio. I turned off XRDP, so I can't have any sort of remote access. And you see my attempts at making Pedalmaster a service. I turned off the VNC server. I stopped ColorD, HCI UART, Cups, the printer server, Avahi, the network discovery. I stopped Trigger Happy, which is a keyboard keyboard hotkey thing. The FWPA supplicant, that's the wireless. What else did I turn off? I turned off Bluetooth. And I don't know. I can't remember how to do. Well, TLDR is a nice little utility that I've installed, which gives you information about a command called, without having to go to the man page and try to figure that out. Oh, as obvious status. So these are the ones I've got running. Not much. So I think I've wandered off into yet another rabbit hole. So that's how the code works. Happy to try to answer any questions. Happy to take any improvements. It's on GitHub. I'll put all the links in the thing, and I've gone for 41 minutes. That's way too long. I'm stopping now. Thank you.